We will see some important FEA concept, that is natural coordinates and Jacobian matrix in this lecture. So we will see like why do we need natural coordinates at first place. So we know the element stiffness matrix for 2D element, okay, which is given by this form, okay, where this T is taken out, it is element section property thickness, and dx dy is our dA, and we have B, D, and B transpose D and B matrices. And to get element stiffness matrix, we need to perform our double integrations over x and y limits. So we have seen element stiffness matrix for perfectly shaped, that is square shape of quadrilateral element in a previous lecture, and also we have taken the element center as a 0 0. So for this element we did. Now let's talk about some general scenario. Okay, so the elements are not always square. There could be some skewed shape. Okay, there could be some rectangular elements or parallelogram elements. The elements might not be at 0 0 always. Okay? They can be anywhere, and element are also can be oriented in xy space. Okay, it is not always that element edges are aligned with the x and y axis. Okay, so for this scenario, let's discuss. Okay, for this element, if I have to write, okay, let's take this is element number one. Let's take this element has some coordinates 2 by 2 2 4 2 4 4 and 2 4. Okay. So for this element, we can write element stiffness matrix 1. We have B D B B D B transpose D and B dx dy. So for this element, the integration limits will be x equal to 2 to 4 and y is equal to 2 to 4. So for this element, it is a straightforward. Okay, but let's take some other element. For example, this element, which is n element number n. So let's assume some coordinates here approximately. Okay. So let's say this is 9 9. This could be no, this could be 10 x coordinate and y coordinates 12. This node coordinate could be 19 11 and 11, and this node coordinate could be 8 and 10. So for this nth element, uh, we can write element stiffness matrix, and we have to determine the x and y limits. So just think about for double integral limits and for a moment. So it is not that straightforward or so easy to determine x and y limits. Okay? So this is the problem with xy coordinates, okay, or global coordinate system. So the all elements, first of all, we need to calculate or compute element stiffness matrix for all the elements. So for all the elements, we need to determine the x and y limits. So all the elements, since they are having different x and y coordinates, they have different limits, different double integral limits. So this is not a big problem, okay. But it is not easy to determine these double integral limits for not so nicely shaped or orient or not so nicely oriented elements, okay, as we have seen in this example. So these are the two issues, and that's where the natural coordinates concept comes into picture. Okay, with natural coordinates, when we write element stiffness matrix, instead of xy space, when we write it into natural coordinate space. Okay, we basically address these issues. Okay, so let's see how it happens. We'll take this element, okay, which is something like this in xy space. Okay, so basically natural coordinates means we basically do a mapping of element from global coordinate system, that is xy, to natural coordinate system. So basically we do a element transformation, okay, coordinate transformation. So natural coordinate system, you can uh, know understand it as something kind of local coordinate system, though it is not exactly local coordinate system, but we can draw similar analogy as a local coordinate system for understanding purpose. Okay, so natural coordinate system is zeta eta. So how it is done, how the mapping is done. So basically we define the natural coordinate or local coordinate system at element center. So this is zeta, okay, and this is eta axis. So we define local or natural coordinates at the element, and it is not only mapping from one to other coordinate system. We also do something else, okay, that is the isolines of zeta and eta. They are aligned with the element edges. So how it is done? We know this zeta axis is also eta equal to 0, and eta axis is zeta equal to 0. So we align the axis, okay, for example this axis, okay, with the sorry this edges with isolines of zeta eta. Okay, so this is zeta equal to 0, and this is zeta equal to 0, this will be a zeta equal to 1. Similarly this will be zeta equal to -1. Okay, this is +1. So we align the zeta lines along the element edges. Similarly, this aspect. Okay, so this is zeta equal to 0. This will be a zeta equal to 1. Sorry, this is eta equal to 0. This is eta equal to 1. Similarly, this element edge is aligned to eta equal to -1. Okay. So we have four bounding lines, okay, zeta equal to -1 plus 1 and eta equal to -1 plus 1. And we can imagine other lines something like this. Okay. So these are basically isolines. So you can say this is eta equal to sorry, this is zeta equal to zero point 0.5, this is zeta equal to -0.5, similarly eta equal to zero point 0.5 and eta equal to -0.5. So basically these limits are important, okay, -1 to 1 and +1, -1 to 1 for zeta and -1 to 1 for eta. So this is our zeta eta coordinates, okay, which is 0 0 this. So when we draw this element, okay, in a local or natural coordinate system, it looks something like this. Okay, this is 0 0. This node will be -1 -1. This node is 1 -1. Okay, similarly other two nodes. Okay. So this is in xy space, okay, and this is in zeta eta space. So we can see that while doing this while using uh, natural coordinate, okay, we can transform uh, the skewed or not nicely oriented element, okay, we can transform it into square and nicely oriented element. Okay, so this element is now 2 by 2 element. Okay, and also it is oriented at 0 0 coordinate in natural coordinate space, okay, zeta eta. So by doing so, if we see, okay, uh, now the element, okay, we need to write element stiffness matrix in zeta eta. Okay, so this is element stiffness matrix which is in z xy. We can write it into zeta eta space. Now the limits, okay, for this element is zeta equal to -1 to 1 and eta equal to -1 to 1. Okay. So this is now very easy. Okay, uh, because we had a issue of not issue of determining the integral limits for uh, not so nicely oriented elements. Okay. So now what are the computational advantages, okay, by using natural coordinates? So all the elements have same integral limits. Okay. So we can see like we have to done the mapping or coordinate transformation for all the elements. Okay. For this element, these are natural coordinates for all the elements, and when we do the transformation, all the elements will have limit of -1 to 1 and -1 to 1. Okay. So all the elements will have same integral limits, because we have to we are now performing integral in zeta eta space. All elements have same shape and size in natural coordinates. So irrespective of any element, okay, let's take this is the smallest element, okay, and this is the largest element. Okay. But when we perform coordinate transformation, all elements will be of square shape, okay, that is 2 by 2. So all the elements have now the same shape and size in natural coordinates, okay, not in global, but yes, in natural coordinates. Similarly, all the elements have same shape functions. Okay, so this we will see in next slide. So our objective is achieved, that now we are able to easily determine the double integral limits. Okay? That is zeta equal to -1 to 1 and eta equal to -1 to 1. So we write now element stiffness matrix from xy to zeta eta. Okay. So this is not no only this much, because there is something we need to perform, because we cannot simply no, change the limits and put it here. Okay, there is something which is changing. If we see B, D and B matrices, okay, last previous lecture we have seen strain displacement matrix, okay, for linear quadrilateral element, which is something like this. So this is basically partial derivatives, right? These are basically a partial derivatives of shape functions with respect to x and y. So this B is partial derivatives of shape functions with respect to x and y coordinates. So now we cannot use this B matrix here. Okay, so we need to transform B, D and B, all the matrices, into natural coordinates. Okay, so B should have partial derivative with respect to zeta and eta space. So these are our shape functions, because B has terms of shape function. They are partial derivatives of shape functions. Okay, and so this we need to transform. Okay, so let's see. So here the concept of Jacobian matrix comes. Let's try to understand. So now we have element into in zeta eta space. So we can write shape functions in zeta eta space. So our shape functions are n1, n2, n3, n4. These are the same shape functions that we discussed in previous lecture, but those were in xy space. Okay, since element we know it is in zeta eta, something like this, so we can use the same shape functions. So we have just replaced xy with zeta eta. Okay. So these are our shape functions in natural coordinates. Okay. Now The displacement, as we know, we have to first do assuming a trial function. So we can write x displacement u and y displacement, okay, something like this: n1 u1 plus n2 u2 plus n3 u3 plus n4 u4, okay? Where n1, n2, n3, n4 are shape functions in natural coordinates zeta, eta. Okay. Similarly, okay, as we said, no, we need to transform this b into zeta eta. This dx dy also we have to write in form of zeta eta. So there should be a relation between xy and zeta eta space. Okay. So this is something given by this form. Okay, let's try to understand this. So x, that means uh, co- uh, the coordinate, the xy coordinate of any point within element is given by this equation. Okay. So this x1, x2, x3, x4 are the nodal coordinates. Okay. Similarly, y1, y2, y3, y4 are nodal y coordinates. So let's try to understand, okay, basically what we are doing here. We see this n1, n2, n3, n4 are shape functions in xy, in zeta, okay, zeta eta. So this is basically a coordinate mapping or transformation from xy to zeta eta, okay? Because we have relation between xy and zeta eta here. So let's try to understand this. Let's take, no, we want to find the center point of this element. Okay, the xy coordinates we want to find for this coordinate, this point. Okay, so x, okay, this point corresponding to no natural coordinates is this one, 0, 0. So x zeta equal to 0 and eta equal to 0. When we put these coordinates, we want to find the corresponding point in xy space. So x coordinate of this point is equal to, okay, n1. Okay, we can put zeta eta equal to 0 here. So n1 will be 1 by 4. Similarly, all n2, n3, n4 are 1 by 4. So here we can put those values. We get x1 plus x2 plus x3 plus x4 by 4. Similarly, y coordinate of this point, which is zeta equal to 0 and eta equal to 0, is y1 plus y2 plus y3 plus y4 divided by 4. And this is very obvious, right? The center point, no, this is center point. So corresponding center point in xy space is a average of x and y coordinates of the nodal points. So basically what I'm trying to say here, this relation, okay, this is basically a coordinate mapping. So uh, it is a mapping of xy into zeta eta. Okay, so the relation between xy and zeta eta space, and that this is what we need further. Okay. So now what we have to do is b, which is dou by dou x, and okay, dou by dou y, we need to transform it into dou by dou zeta and dou by dou eta. Okay. Similarly, dx dy into d zeta d eta. So x to zeta and xy to zeta eta. Okay. So we already have got the relation, right? That is coordinate mapping xy into xy relation with the zeta eta. So we will use the chain rule and find the relation of xy derivatives, I mean derivatives with respect to xy to derivatives with respect to zeta eta. So we'll use a chain rule. We know x and y function of zeta and eta. So let's check this is any function. Okay, the partial derivative with respect to zeta, dou by dou zeta is equal to, uh, since this function, okay, this could be anything, u, not u but b. Okay, let's check this is a b. Okay, or uh, the terms of a b. Okay, so let's say this is something like this. So dou by dou x, okay, of b, because b in global we have with respect to xy. Okay, dou by dou x into dou x by dou zeta. So b in xy form and x in as a function of zeta eta we have. So using this we can find the dou of b with respect to dou zeta, plus similarly other dou by dou y into dou y by dou zeta. So this is a chain rule. Let's use this chain rule here. Okay, let's remove y u here. Let's put it for any general. Okay, so dou by dou zeta, okay, here is equal to dou x by dou zeta plus dou by dou y uh, dou y by dou zeta. Okay. Similarly, with respect to eta, dou by dou eta is equal to dou by dou x by dou eta plus dou by dou y by dou eta. We can write this in a matrix form. So this same equations in a matrix form. We get something like this, where this left hand side is, okay, these are the partial derivative of any function, okay, with respect to zeta and eta. Okay, so partial derivative with respect to zeta and eta, and here we have partial derivatives with respect to x and y. So now we got the relation. Okay, this here in previous slide we have relation between xy and zeta eta space. Here we have partial derivatives relation. So this is called J, and it is also called Jacobian of element stiffness matrix. Okay, or it is also called simply Jacobian matrix. Okay. So just rearranging the terms. Okay, dou by dou x and dou by dou y is equal to J inverse dou by dou zeta dou by dou eta. Okay. So now the B matrix, okay, which has dou by dou x and dou by dou y, using this relationship, can simply transform B matrix into dou zeta and dou eta using this relation. Okay, so, so that is what the Jacobian matrix significance is. Okay, and now the element stiffness matrix. Okay, let's come back to element stiffness matrix, which has B, D, and B. Okay, this will become B dash, okay, because now B dash, okay, is in form of dou by dou zeta and dou by dou eta. So B dash and B dash. So these two are there. So what about D matrix? Okay. So the D matrix will not change, because we know the D matrix is stress strain relationship. Okay. It is it depends. I mean, whether it's a 2D or 3D case. So it has nothing to do with element. It has to do with the dimensionality of problem, right? Of problem or space. So D will not change, only B will transform. Okay, so it will be B dash. Okay, and dx dy will be determinant of this matrix J into d zeta d eta. So let's we can derive this as well, but let's not do it. Okay, as FEA engineer we don't need the derivation of that. So, but let's try to understand what exactly this. So dx dy, dx dy is equal to determinant of Jacobian matrix d zeta d eta. So what exactly Jacobian? So J is basically shape or size factor. When we transform the element from know, original coordinate system to natural coordinates, because if we remember, okay, we have this xy space, okay, we have element, any any element something like this, okay, let's take this element is something like this, and when we transform this from xy to zeta eta, they all are square shape with the same size, 2 by 2. So basically, we know the Jacobian matrix is a relation between xy, that is basically coordinate mapping. So we can say it is a basically shape or size vector, okay, because the Jacobian value, okay, it shows, okay, when this, I mean reverse, okay, when uh, sorry, so the Jacobian basically, uh, it basically expands or shrinks, right? Because the smaller element will become a big 2 by 2, and very big element will also become 2 by 2. So either it shrinks or expands, okay? So that's what we are saying, it is a size factor, okay, and it is also shape factor, because the skewed element, okay, whatever skewed element it is, whether it's a skewed or parallelogram or rectangular element in xy space, they all become square elements, okay. So it is basically also shape factor, because it shows like how much the shape is how much distorted shape uh, is turning into square shape, okay. So it is basically a square shape factor, and that's how no, we also see the Jacobian of elements, okay. They are also treated as a element quality parameters in some softwares, because it shows how it strings or expands, and how it gets skewed, unskewed, okay. So with that, I hope this is clear, okay, what is the purpose of Jacobian and natural coordinates. Let's recap quickly. The natural coordinates we are using because with the global coordinates we have issues with double integral limits, okay, and with natural coordinate we have all the elements with same integral limits, that is zeta equal to -1 to 1 and eta equal to -1 to 1, and when we transform the elements to natural coordinates, all the elements will have same shape and size, okay, and also have same shape functions. So that is the computational advantage with the natural coordinates. So the Jacobian matrix we have because we want to transform the element stiffness matrix from dx dy to d zeta d eta, and also B matrix, which has partial derivatives respect to xy, we want to transform them into uh, partial derivatives with respect to zeta eta. So for that purpose, we have a Jacobian matrix. Okay. And this is our final K matrix, which is from dx dy to d zeta d eta. Okay. The xy limits earlier, which were not easily determined. Okay. Now it is very easy to determine, and those are zeta equal to -1 to 1, eta equal to -1 to 1. And additionally, we will have Jacobian, okay, uh, which is dx dy equal to Jacobian, determinant of Jacobian matrix into d zeta d eta. And similarly, we need to transform B from xy space to B in zeta eta space. So this is a summary of what we discussed.